Okay, AP Statistics. In front of me are 5 pages of notes for Section 6.2. I don't think I'm up for doing all those in one day, so we're going to stop somewhere in the middle of this. I think I got a good place to stop. I could stop just after the first 2 pages, but that third page is a monster, so I think I want to get started. The fourth page is a monster, sorry. I think I want to get us through at least half of the third page here. So here we go. Roll up your sleeves, and let's talk about transforming and combining random variables. Now, so far, with discrete random variables, when you get the chart, it's discrete because there's a countable number of options, right? We have found the mean and the standard deviation and interpreted the mean and standard deviation. Then we moved on to a continuous random variable, and we looked at, like a uniform distribution and a normal curve. Well, now, I'm not just looking at one random variable, I'm transforming it with numbers, or I'm combining a couple of them. So here we go. I'm going to roll a die as a gambling thing. If I roll a 1 or a 6, I get 10 bucks. If I roll a 2, 3, 4, or 5, I get nothing. So I'm more likely to win nothing than I am to win $10. We could just try and figure out how much to charge for this so that people will think it's worth it, or so that we would make a whole lot of money if we're running the game, or if we're gambling, if it's a good gamble or a bad gamble. Right now, we're going to ignore how much you pay to play, and we're only going to consider the winnings as a result of rolling this die and seeing if you win money or not. Maybe not the most exciting gambling game ever made, but you guys get the idea. The probability, if I call X the number that you win, the amount that you win, it's a random variable. And since it's a countable number of options, it's a discrete random variable. Now, what's the probability I get $0 out of this thing? I could roll a 2, 3, 4, 5. That is 4/6. What's the probability that I win the 10 bucks? Well, that's a 1 or a 6. That's 2/6. You've done very well so far. I'm very proud of you. Now, I'm going to find the expected value. Well, that's the mean of X, and we found out the other day that that is 0 times 4/6 plus 10 times 2/6, which is really, let's see, that's 20/6. If I multiply that out, that's 3 2/3, I think. So that's, we'll call this, is it 3 2/3? 6, 18, 19, 3 2/6. That's 1/3, $3.33. Just talking out loud here, stubbornly not using my calculator. Find the standard deviation. Always a little more work, but it makes sense when we're done with it. So I'll write small. Here we go. Sigma is the big square root of two things. 0 minus $3.33 squared, but it's got to be times 4/6. Do that sideways like that. And then plus, then we'll go $10 minus $3.33 squared. Notice since I square, both will be positive, so that we just add to the standard deviation and show how spread out this is. This would be times 2/6. Okay, I definitely went to the calculator on that one, and I got $4.71. Now, if this was section 6.1, I would ask you to find those and interpret them. So we're gonna. If I heroically roll this die many times and play this over and over and over and keep track of how much I win, the average I expect to win is $3.33. So what does that mean? If I'm running this as a gambling game and I'm trying to make money, I want to charge people more than $3.33 because I'm expecting to pay out $3.33 over the long run. Maybe I should charge like $4 a game to play. So some people are going to walk away with 10 bucks and feel like hey, this is a great game. I paid $4 and I got $10. I made $6 by rolling a die. But most people aren't going to get $10. Most people are going to get $0, and I'm taking $4 from them. In the long run, I'm winning out. What I don't want to do is charge $1 to play the game. Because even though most people get 0 and I get to keep their dollar, the people who do roll the 10, they get to take $10 away from me. And the average I'm paying out is $3.33. I don't want to take $1 from every person, or in the long run, I'm losing money. If I want to run something called a fair game, which I will write up here just so you guys see it. If I want to play a fair game, then what am I going to do? I'm going to charge $3.33. Now, that's not what you do when you run a casino, because nobody's interested in playing fair games when you run a casino. You want to charge more so that in the long run you make more. Just teaching you guys how to gamble, no big deal. Anyway, gambling by rolling a die. Now, if you pay $1 to play, consider something called the net gain. What that means is if you pay $1 and you win, you get $10, but you paid $1, so you really came away with $9, right? You gained $9. If you give $1 and you lose, you're negative $1. So let's go to the x's here, and I could have -1 or I could have $9 as a result of me paying $1 just to start. The probability of the -1 is 4/6, and the probability of the 9 is 2/6. Find the expected value. Now, of course, guys, I'm going to find these. I'm going to compare with those. Doesn't it make sense to compare and see what happens to x when I subtract $1? This should start to sound kind of familiar to you. What happens if I subtract 1 from every x value? What happens to the mean? What happens to the standard deviation? We've had this conversation before, just not with discrete random variables. Okay. The expected value, mu of x, is going to equal -1 times 4/6 plus 9 times 2/6. Okay, that's going to be -4/6 plus 18/6. I think that's 14/6. Am I doing that right? So that's 2 1/3. So dollar sign right there. So 2 2/6, which is 2 1/3. So it's $2.33. Find the standard deviation. Now, those of you who are smart already looked somewhere on the page and made a connection. Some of you are like, wow, this is fun. Find the standard deviation goes like this. Sigma of x equals a big giant square root. And I'm going to go -1 minus the mean of $2.33 squared. That's going to be times 4/6. And then I'll do the second one, and it'll go 9 minus $2.33, and it'll be squared. And this will be times 2/6. I clearly made my square root thing too long. When I put that all in the calculator, which I just did a minute ago, I get $4.71. And those of you who already looked at something else on the page went to look at something else on the page when I did that one and just confirmed what you thought was going to happen. That's how smart you are. Look at the mean. What happened to the mean when I subtracted 1 from every x value? I subtracted 1 from the mean. Didn't we know that was going to happen? When I subtracted 1 from each x value, what happened to the standard deviation? Nothing, because when you add or subtract to every x value, it doesn't affect the standard deviation. Doesn't that sound familiar? So let's write it down. Compare the two means and two standard deviations. When you add the same number to all x values, just like in chapter 1, I think it was chapter 1, maybe chapter 2, you can just add that number to the mean. So you can shortcut changing these x values and then redoing this mean process by just going, hey, I think I just subtract 1. I'm pretty sure I learned that somewhere. But the standard deviation doesn't change. If you add or subtract the same thing to every x value, measures of spread do not change. You knew that. Go to the next page. Shame on you.